saw that you evaluate also the reaction force of these two values, but that's not right.
Oh, it just seems the same, yeah.
Yeah, like you don't use these when you're trying to find the absolute
Just use
shear
the
stress.
internal ones, right?
Just use the internal ones, so just the four.
Actually, I'm going to start on it.
Yeah. I'm gonna have to work on it, fix it after that. He accepted the deadline. He made it due tomorrow.
Oh, for real? 26? ايه ده فين؟ ده عمري حتى ألف غيري.
Just a relief over here.
Someone's like talking over the time.
Close
So
enough.
الحمد لله ليك ده لو ما كانش فيه extension. كان زماني مهلبية. ده جايب زيرو من كل خالص. بجد زماني كنت فاهم فيه ولا؟
I was just trying to fix work.
Huh?
I was just trying to fix work.
2020?
I couldn't grab the
But
last one.
do you think your last 3 pounds were the bending ones?
The last part C, I don't know how to do that yet.
But the ones before.
I think those are right.
Okay, good morning everyone. Good morning. So I want to solve one more problem on shear force and bending moment diagrams. And then we will move on to bending stresses. Okay? This problem is present in your pre-lecture slides as well, along with the solution. I just want to do the solution here together with you all. Okay? So this is a problem where you have an overhanging beam. Overhanging beam, I'll draw it out and then explain it. Is similar to a simply supported beam, the only difference being that one of the supports will not be at the end of the beam. It will be somewhere before the end of the beam, which means that there is a small portion of this beam that's kind of overhanging away from the support. And here is a loading situation on this beam. Okay, so I have an applied load which has a magnitude of 200 pounds. Then I have a distributed triangular load. Please notice the intensity of this load distribution is pointing vertically up, as opposed to what we have been doing in the past. It was pointing down. So this is 100 pound per feet, the intensity of the largest arrow there. I have a concentrated couple moment at the end of the beam, which has a magnitude of 200 pound-feet. And here are the distances for us. This is, I think, 2 feet. 3 feet and 3 feet, and I have the pinned end called as A, and the end where the roller is present, or the place where the roller support is present, is called as B. Okay, so this is A, and this is B. Can everybody see my writing clearly? People in the back? Is this kind of bothering the dark space here? Somewhat. I can't do much, I'm not that tall. Perhaps that helped. Okay. So we want to draw the shear force bending moment diagrams without doing any undue calculations necessary to draw. Bending moment diagram, and from these I need to obtain the maximum values of the shear force in the bending. Okay, so obtain V max and M max values. As I said, your first step is always obtaining the support reactions. We are not going to spend time obtaining support reactions. Okay, I have the details shown in the lecture notes posted. Here are the support reactions we will obtain if you do the calculations. At A, the pen will exert an upward support force of 110 pounds. Obviously there are no forces in the X direction for A. Then at B, watch out, look at the calculations, I've posted it on your Carmen page, you can take a look at it later. At B, the support reaction will be pointing vertically down. Okay, if you go through the calculations. And this magnitude will be 60 pounds. The first step in all these problems, obtain the support reactions. Then we will start off with the shear force type. X, this will be in so many feet, okay? And then I'm going to have V in pounds. And I have a couple of stopover points. X is equal to 0. Okay, so this is X is equal to 0, X is equal to 2, X is equal to 5, and X is equal to 8. Okay, so those are my points of interest. So 0, 2, 5, and 8. Help me out here. At A, what should the shear force diagram be doing? It should be pointing vertically up because of the fact that there is an upward concentrated force acting here. Okay, so this is going to be pointing up. It's going to stop at the magnitude of 110 pounds. Okay. Then as I go from A all the way to where the force is acting, the 200-pound force is acting, I stop short of that. Okay. And where do I end up? I stay at 110 all the way. Then I see that there is a force of magnitude 200 pounds which is acting in the downward direction, which means that this is going to push me down by the difference between 200 and 110 pounds. Okay, so all the way down to minus 90 pounds. Does this make sense to everybody? Why am I going as a straight line from here all the way to x is equal to 2? Is because of the fact that as I look from A to where this force is acting, there is no distributed load there. So the slope of the shear force diagram is 0. And so I have to travel constantly. I drop down by the difference between 200 and 110 pounds, which is minus 90. Then I see that from here all the way to where this force is acting. So many things are taking place starting from point B. There is a force acting vertically down, there is a distributed load acting This guy does not do much to my shear force diagram, so I can leave that alone. It has been taken care of when I calculate the support reactions. So as I go from x is equal to 2 feet to x is equal to 5 feet, I'm going to be first of all traveling as minus 90 pounds until I reach the force of 60 pounds which is pushing me down further. Okay, so I travel down this way. And the force of 60 pounds which is acting at the point B is going to push me down further because it is acting in the vertically downward direction. So that's going to be 60 plus 90, which will take me to 150 pounds negative. Does this make sense to everybody? Are there any questions so far? The only calculations that we've done so far is calculate the support reactions. And then just by looking at the nature of how the load is acting, if I have a concentrated force, the shear force diagram will see a jump either up or down. If the force is acting up, shear force diagram will see a jump up. If the force is acting down, it will see a jump down between where it was previously and where it is now. Then I need to go back to zero. I first of all make sure that everything works out for me. I am currently at minus 150 pounds, right, which is at this point here. I calculate the area under the distributed load. What's the area under the distributed load? It's half times 100 times 3. Is it a positive or a negative area? It's a positive area because the W of x, the intensity is pointing vertically up. So that's going to give me plus 150. I am at minus 150. So at the end of the beam, I'm going to go back to 0. Does this make sense to everybody? The only question is, how do I go to 0? And that's where we have to be careful. If I look at the distributed loading is first of all positive, and the intensity of this load distribution reduces to 0. So which means I start off by saying that first of all I'm going to be increasing, so I'm going to go from a negative value to a less negative value, which is essentially 0. And how am I going to go? Decreasing slope, eventually going back to 0. Okay, so right here, this is going to be the manner of the shear force diagram, and it's going to be a quadratic. This is because the slope is decreasing linearly. Okay, so between x is equal to 5 feet and x is equal to 8 feet, the dV by dx value is first of all positive. So I see that I have a positive slope, it's pointing up as I go from 5 feet to 8 feet. So dV by dx is positive. Why is it positive? It's because the load intensity is acting vertically up instead of down. And then the magnitude of the slope is going to be decreasing all the way to 0 because the magnitude of the load intensity starts from some non-zero value, goes all the way to 0. So this is positive and decreasing. At 8 feet. And if the slope is decreasing in a linear manner, so this is a linear decrease, the curve is going to be 1 degree higher than the slope, so this is going to be a quadratic. Okay, so you've got to label that this is a quadratic. This is because the slope is decreasing linearly. Questions on this? Yes, sir.
I'm just wondering, like, what is a an increase to be linear instead of like a quadratic one? Like, because I thought distributed loads were given a linear increase rather than like quadratic increase.
Alright, so you could have a distributed load as a quadratic distributed load. The load itself could be a quadratic. Right? So all we have in this class and probably for the rest of your undergraduate career you will be seeing only two types of distributed loads, a rectangular one, a triangular one, or a combination of the two. So from that point of view, if you have a triangular distributed load, the intensity is decreasing or increasing linearly. If I have a uniform rectangular distributed load, the intensity is constant. Besides these, you will not be seeing any other things. And so if I have a rectangular distributed load, I'm going to be going in a linear fashion in the curve for the shear force diagram. If I have a triangular distributed load, I'm going to be going in a quadratic fashion. Yes, yes.
So for the homework that's due today, for when we're drawing the shear force diagram, do you want us to like write out all the x's, or can we just kind of like explain how based on like the original diagram, like how the like jumps and curves?
That's a good question. I would like to see at least one or two problems handled with the more detailed explanation so that you get used to it. And then, I mean, I know that probably all of us are more or less used to it, so you could do it this way. Yeah. Yes.
In recitation, we like solve for v of x and m of x, like between like certain segments.
Don't do that.
We don't need to do that.
Don't do that at all. Yeah. No solutions to be given, right? I mean, no solving of any sort. Your aim is to make your life as painless as possible. Okay? You just look at this guy, you draw this guy. And my only question to all of you is everybody on board with what I'm talking about here? Can you all see the relationship between this curve drawn here and this one here? I want to see if there are any questions before we draw the bending moment curve. Slightly more trickier than this one. Okay. Follow what I do in class. I have told your recitation TAs to also follow what I do in class, but sometimes they don't come to class, like you see. So that's what happens, but I'll make sure that they understand what's going on here as well, okay, just to be on the same page. Because what happens is that in real life, you're going to be inspecting a bridge, for example. You're a structural engineer, you'll be inspecting a bridge. You'll be seeing all manners of loads acting on the bridge. One will not necessarily have, and the bridge will be pretty long. One will not have the time to keep sectioning at multiple places and then figure out what the nature of the distribution of the shear force in a bending diagram is. You will have to do a freehand sketch on the back of the envelope standing under 110-degree heat in New Mexico or something. Okay? So you want to be able to do these things in a optimized manner, in a very efficient manner. Right? So that's the reason why I kind of press this. It might be initially some growing pains, but once you distinguish, okay, there is nothing going on here. If I see a force pointing up or down, it's just a jump up or down. If I see a distributed load, it's going to change the nature of the curve. That's about it. Okay? And if I see a couple moment, it's not going to do anything to my shear force diagram. It has already done its duty. Okay, it has done its due diligence in helping us calculate the support reaction. So it would have had its effect on the calculation of those things. Okay? So we'll go to the bending moment and then we'll move on from there. So this is in pound feet. I first of all mark off all my locations. Okay, so this is 0, 2, 5, 8. So this is the total distance was 2 feet here. This distance is 3 feet. Okay, and then the last part is 3 feet. Alright, so I start off by looking at the beam first. So when you're drawing the bending moment diagram, you need both, right? I start off by looking at the beam. Is there any couple moment acting at the end A? There is nothing. So it means I start at C. In your problem in the homework, you have a cantilevered beam, which means that you will not be starting at 0, you will be starting at a non-zero value of the bending moment. Okay? Then I go from point A to the next point, which is 2 feet away. The value of the bending moment is going to be the area under the shear force diagram. This is a positive area. This is because it is 110 times 2, so around 220 pound-feet. It's a positive area because I'm looking at the shear force value above the x-axis. Okay, so this is 220, which is the area under the shear force diagram. That's going to be the value here. The only issue is how do I go from the start of the beam all the way to that point is by looking at the slope of the bending moment curve. The slope of the bending moment curve has to be the value of the shear force, right? So dm by dx is v of x. The value of the shear force is constant, which means, and constant and positive, which means that my slope dm by dx is constant and positive, so the curve is going to be a linear increase from 0 to 220. Make sense to everybody? Then I go from x is equal to 2 feet to x is equal to 5 feet. I immediately recognize that, okay, the area that I'm looking at is this rectangular box. This rectangular box is now below the x-axis, so that's going to be a negative area. Okay? So that's going to take 90 times 3, so that's 270. I had 220. This was negative 270 plus 220 is minus 50 pound-feet. This is the value here. How do I go from where I had stopped at 220 pound-feet to minus 50 pound-feet? I look at the slope of the bending moment diagram. It's equal to the value of the shear force, which is negative. So I am descending linearly because the slope is negative and constant. The zero crossing point in a bending moment diagram is of not much consequence to me, so I don't worry about calculating that crossover point. Okay. Questions so far? Everybody on the same page? Yes, sir.
Wait, how do you get the negative 50?
Oh, how did I get it? Is by taking this 220, which was the value here, and then the value here is going to be this value plus the area under the shear force diagram, which is going to be 90 times 3 but to the negative value. So minus 270 plus 220. Now I'm going to need your help. How do I complete the diagram? Of course, you have the completed diagram on your pre-lecture slides, but how did I do it? Any takers? Or here is the question that I want to ask. At the end of the beam, what are the things that are going to happen? First of all, I see that there is a clockwise couple moment of 200 pound-feet. A clockwise couple moment in a bending moment diagram is going to do what? It's going to take the bending moment value and push it up. It's a singularity that is taking place. So which means that I should have been, before seeing this guy, I should have been at a value of minus 200 pound-feet in my bending moment diagram. Am I right? We are going to see. Okay, so I'm going to just mark minus 200. I should have been here. How am I going to check and see if I am actually there? Is by doing the following. Forget the presence of this guy. Okay, for the time being, forget the presence of that guy. Find the moment caused by all the other forces if I cut off the beam right before I hit the end of the beam. What's that value going to be? It's going to be 110 times a distance of 8, and that's going to be in the clockwise sense. Okay, so I'm essentially summing moment at the end just before the 200 pound-feet. Okay, I'm doing that just before the 200 pound-feet couple moment, so I'm just looking at the total sum. It should give me what? 200, hopefully negative or positive, we'll see. So that's going to be 110 times 8 clockwise. Then I'm going to have 200 pounds times a distance of 6 counterclockwise. I'm summing moments about the end of the beam, so this is plus 200 times 6. 60 pounds times a distance of 3 feet. Am I making sense to everybody so far? You see what I'm doing? I don't know if this is going to be at minus 200 pound-feet. I could do the following. I could calculate the area under this quadratic curve. Who wants to do that? Not me. So I want to make sure that my calculations are indeed right, that it takes me to minus 200 pound-feet, and then the couple moment will act and push me back home. Okay, that's what I'm trying to find out. I'm summing moments at the end of the beam, right before the 200 pound-feet couple moment. So I'm not including its action on the calculations yet. 60 times 3. Triangular distributed load can be replaced by a single equivalent force. That's going to be area under the distributed load, so 150 pound-feet. Where does it act? 2 times the base of the triangle from the pointed end. So this distance is 2 feet. So 150 times 2 clockwise. If you do the calculations, it's going to end up giving me minus 200 pound-feet. Which means that this is the value of the bending moment right before I hit the end of the beam. Not inclusive of the 200 pound-foot couple moment. So indeed our calculations are correct. Everything is falling into place. Am I making sense to everybody? Do you see the purpose of what I'm doing here? And so since I know that we are getting the same answer as we are expecting, we are good to go. The only thing is, how do I go from minus 50 to 200? Look at the shear force diagram. Slope of the bending moment is the shear force value. Shear force value is what? Is it positive or negative? Negative. Slope is decreasing. Which means that I start off with the same slope that I had here. Slope is decreasing and eventually goes to 0 at the end there. So I'm going to go in the following manner on the bending moment curve. What kind of a curve is this going to be? Is it a quadratic or a cubic? It has to be a cubic because the slope of the bending moment is a quadratic. And then I go back home. Because of the fact that I have a 200 pound-foot couple moment pushing me back up. Okay, so this is going to be a cubic. So between x is equal to 5 feet, x is equal to 8 feet, dl by dx is negative, which means that I'm dropping down, negative slope, and it is decreasing in a quadratic manner. It is decreasing quadratically to 0 at 8 feet. And so the curve is going to be a cubic, which will start at the same slope, continuity. And then it will keep going. The slope is decreasing, as you can see, and then eventually the slope becomes equal to 0. Then it pushes back. This is the bending moment. Right? Any questions? Yes, sir.
So when you take this sum of the moment, I got it. So it's 200 pounds. So how does that? So is it because we're assuming that that moment is clockwise? So it's like we're like switching it, making it that one is negative, that one's the positive, and then making them equal.
No. So what I'm saying is, in the bending moment diagram, the value of the bending moment at that particular point, right before I hit the end of the beam, is minus 200 pound.
No, I know, but when you calculated the sum of the moments, it should be 200 because it should be positive 200. If you do the clockwise, counterclockwise is positive.
Right. This will end up being positive. Yeah, I'm sorry.
Yeah.
I'm sorry. Yeah.
So we're just assuming that it's the opposite of it.
Right. Absolutely. Right. That's right. Yeah. Okay. So what's the largest value of the shear force and what's the largest value of the bending moment? You've got to be careful here. The largest value of the shear force is 150 pounds with a negative sign. Okay, so V max is minus 150 pounds, and you're going to see the meaning of this negative sign. Essentially, it says that you're now in a direction opposite to the positive sign convention at that location. That's all it says. The value of the largest bending moment is 220 pound-feet positive. And max is plus. Which makes absolute sense, because this is the point of zero crossing for the shear force diagram. So the maximum bending moment value has to occur at that particular point. Isn't that what it is? Right? So this is the point of zero crossing. Okay, so I just have one request from one of you. Could you take pictures of these chalkboard and then email it to me? And I'll post it on Carmen page along with the video as well, okay, just so that you have a reference. Thank you. Okay, last questions on shear force and bending moment diagram. We're going to go on a completely different journey from now on. We will make use of these. We are not going to spend time drawing these out because now we know a very quick way of capturing these evolutions or a function of distance. Okay. Last question. When you draw the shear force bending moment diagrams, let's say in an exam, what are the things I need to see? I need to see the support reactions calculated, first step. Then I need to see, okay, if there is a point of zero crossing, label that. If there are pieces that are not regular, which means that if there is a quadratic or a cubic or so on, then tell me how you obtain this quadratic by showing this is how the slope evolution took place. Okay? You don't need to show me anything else. And on the bending moment diagram, you've got to tell me, okay, this is a cubic piece. Why is it cubic? Because of the fact that this is what is happening for the slope of the bending moment diagram. Do my values add up? You've got to show me that too. Okay, so those are only the three things that I require of you, please. Support reactions, draw the figures. If you see something abnormal taking place, curves of some kind, quadratic or cubic, specify what they are and tell me why they are occurring. And if there are points of zero crossings, tell me what they are. Sometimes it's evident. Sometimes you might see a linear drop and you have to calculate the zero crossing using the similar triangle idea. Okay? Question?
You only want us to label zero crossing in the shear one, not the.
Not on the bending, absolutely. Yeah, because this is of, at least for the time being, it doesn't make any difference. Okay, so I'm going to move on to bending theory, or beam theory as they call it. What I'm going to do is, half of this lecture, most of next lecture, I'm going to do two topics at once. So that we do real situations in life, which are combined loading. That is, I'm going to take a beam, throw the zinc at it, and then see, okay, what's going to happen to the body. Okay? So I'm not going to do piecewise like what your textbook does. They do bending theory first, and then they do transfer shear stress. I'm going to do both of them in one fell swoop, and then we're going to attack real problems. Okay? All right. There will be some derivations involved. I won't be doing all of them. Whatever I don't do, I will post it on card for those who are interested. Today we are going to focus on bending stresses. Obviously, bending stresses are caused due to bending moments. Common sense, right? That's why we are doing all these things. Before doing that, I want to refresh our positive sign convention. Concave upwards is positive for the bending moments. If I look at a beam, if this is the direction of the bending moment, cut on the beam, then this is concave upwards, this is the positive sign convention. So in this case, I'm going to say that my M is positive. Obviously, the inversion of that is going to be my negative sign convention. If I have a situation of this sort, then my value of the bending moment is going to be negative M. Okay, so this is the negative sign convention. And beam theory, as the name implies, employs beams. Beams are any bodies that have a very, very long length compared to any of their cross-sectional dimensions. Okay, we've gone through this sometime back. I'm going to first draw a beam without any loads acting on it and mark certain things on the beam. Okay? Let's say that I have a simply supported beam. First thing is x along the x-axis, starting from left to right. Okay, that's a typical notation. Y along the y-axis. Watch this. My y value is going to start from the centroidal axis. So in statics, you would have learned about centroids. You would have learned about moments of inertia. The use of the centroids is going to come of relevance now. Okay, this is why you're learning about centroids. So bear with me for the time being. This is the y-axis. I'm going to draw vertical line segments on the beam. Okay, so these are vertical lines. Then I'm going to draw horizontal fibers. Okay, so those are horizontal fibers. And I'm going to label the length of the beam as capital L all the time.